So I've been spent some time recently playing around with Kubernetes on Azure, mainly because Microsoft was kind enough to give us some free credits. And I've been diligently using these credits by launching a bunch of servers in Kubernetes. So if you're not familiar with Kubernetes, it's a system to manage cloud computation, let's say, right? If we go to the Microsoft Azure portal, there's the Kubernetes service. And can you guys see my screen?
Yeah.
Yeah. I have something called HS test cluster. And if we go in here, we see there are some property settings and something called node pools. So node pools are basically clusters of VMs. And there's actually 3 node pools. You go in here. There is, how do I see my node pools? So yeah, there's this agent pool. This is set up when you create the cluster, and it's basically machines that are used to manage the Kubernetes service itself. Though they can also run your user pods. And what are pods? Pods are the minimal unit of deployment in Kubernetes. So you define a pod. A pod has a basically container image and configuration, and you tell Kubernetes, I want to run this pod. And Kubernetes will find, hopefully, one of these VMs in one of the node pools that has sufficient available resources to run your pod. So the nice thing about Kubernetes is that you're not futzing with saying, I want to run this process on this particular VM. You leave all that up to Kubernetes, right? You say, I have a bunch of processes, go ahead, figure it out, and get those running. So anyway, there's this worker pool. And this one is using a fairly small machine. It's called a standard D4 V3, which I think is like 8 gigs of RAM and 1 core. There's also something it's enabled for spot instance. So spot instance is basically a machine type that is cheaper, which is good, but you don't have guaranteed availability, meaning that there's more demand for these machines. Microsoft may yank that machine out from under you, right? So any kind of pods you have running on a machine would get terminated, which is fine, for some certain workloads, maybe not fine for others. And then I have another node pool called Worker 32. And this one is using called the standard D32ASV5. So this is a machine that has 128 gigs of memory and I think 32 cores per machine. And the interesting thing is that you have this button here to scale your node pool. Okay, so now I have 4 nodes in this node pool. And if I want to say, have 5, I can just press 5 here and say apply, and it will automatically provision a new machine. And once that machine is online, it takes a couple of minutes, that machine would be available to run any of your pods. Okay, so that's basically kind of the setup of Kubernetes. Now, how the heck do we run things on it? Well, I just recently updated the user guide. If you go to HDF Group HSDS docs, Kubernetes install Azure, there are instructions from how you do. So there's a few things you need here, right? You create this Azure environment. You create secrets. So secrets in Kubernetes are a way to have information that you don't want publicly shared available to your pods. So this Azure connection string is basically like a password for your service. So you wouldn't want anyone who's connecting that machine to be able to see that value, so it can be stored as a secret, so it's not immediately visible. Sorry. And then this RBAC role is a bit particular to HSDS. The RBAC role lets pods discover other HSDS pods. So one of the things about HSDS running Kubernetes is that you can run HSDS in just one pod or any number of pods up to the amount that your cluster can support. And these pods are able to talk to the other pods. So when a request comes in that spans multiple chunks, the first pod to get a request multiplexes out to the other pods. So they can all be working to this request. And we'll see how that affects performance in a bit. Anyway, so this RBAC role is basically a permission that lets a pod running in Kubernetes call this pod list function to find out what other pods are running in that cluster. And then you have a Kubernetes service. So the service defines the endpoint of your application, right? Here we create a service called HSDS, and so this type of load balancer. What that means is that it creates an external IP address. So you have this cluster IP, and which is only visible within the cluster, and an external IP that's visible publicly. So anyone, if you define this external IP, can use this IP to connect to the HSDS service. Okay, the service by itself doesn't instantiate any pods. So when you create the service, at first there'll be no pods to back that up. So any requests to this endpoint would fail. But as you create pods, this load balancer is going to distribute those requests among the available pods. Okay, so if you have a service that's getting 10 requests per second, maybe one pod is sufficient. If you're getting 1,000 requests per second, you want to scale up the number of pods. And then those pods can be all working to process those requests. Another Kubernetes thing is config maps, right? So running an application is not just code, it's also configuration is important. In this case, configuration would include things like the bucket name. In Azure speak would be the container name, where the passwords would be, what endpoint to use, and so on. You create this container image, and then there is something called the K8s deployment. So a deployment in Kubernetes tells you that how to instantiate your pods. So if we look here, I have a K8s deployment that I modified slightly from the example. But if you look through here, it's a kind deployment, HSDS, and the image that will pull off of Docker Hub. how much memory it should use, what volumes are kind of like virtual file systems, what container port to use. This liveness probe is interesting. So liveness probe is basically, if this is set, Kubernetes will periodically ping that pod to see if it's still healthy. So it'll call this info request every 5 seconds. If the pod fails to respond with the 200, Kubernetes will decide that pod has gotten sick for some reason and disconnect it from the load balancer. We have another container for the what's called the DN container, pretty much the same stuff. And then these volumes, right? So the accounts are used for user password information. Config is the config map, and override are basically modifications to the standard configuration. Okay, so that's all nice. So here, so in Kubernetes, the magic command is kubectl. If I do get deployments, I see there's one deployment, it's called HSDS. And I could say delete this deployment, that's no big deal. Okay, so now it's gone. And now I can create the deployment again. Like this. Okay. So now I have a deployment, and I actually have some pods. Okay, so by default, there's one pod. There is, if I run hsinfo, it's going to call this endpoint. This was the public endpoint we saw earlier. And it responds, says there's one node. In case of Kubernetes, that means one pod. It's been up for 20 seconds. If I wanted to scale up Kubernetes to run more pods, to do more work, there's a command for that. I can't remember all these commands, so I usually make these little cheat scripts. So it's kubectl scale replicas some number for the deployment. So if I say scale HSDS 16, and now we do the get pods again. Oops. I have 16 running pods. Okay, and if I do hsinfo, I see node count now is 16, right? So that means for any requests up to 16 pods, which is basically 16 cores, can be used to process that request. In addition, you can process more requests simultaneously. Okay, so that's interesting, right? Let's have a little demo here to show how this can work. And to do this, I have another script called basically another deployment I call hsperf. And what this does, let me just look at the code here. If hsperf is a kind of deployment called a job. Okay, jobs are distinct from deployments in Kubernetes in that whereas a pod and deployment just runs forever until you shut down, a job runs until it's out of work to do, and then it stops, right? So if you have like a fixed amount of work to do, you could create a job, a Kubernetes job, it would go through its work, and once the work is done, the job is done. So basically batch processing for Kubernetes. And what's the work? Well, we're going to have create a HSDS domain basically a file, with a data set. And the data set will have a defined number of rows and columns. And the worker pods are going to be initializing this data set. Okay, so normally in a single process kind of thing, you would say, for each chunk, I'll write this chunk to initialize the whole data set, some predefined values. If we want to utilize the parallelism of Kubernetes, it's a little more complicated, right? We need to create multiple of these job pods and direct the pods to modify our target data. Then that brings a challenge, right? How do you coordinate these worker pods, right? You have some number of worker pods. You want them to divvy up, in this case, the data set, and each initialize their part of the job. And if I imagine like an MPI script, you would use, say, the rank to kind of partition the data set, and that would all happen. In Kubernetes, we don't have that mechanism, so we have to kind of do our own thing here. And what I do in this case is I create an additional data set called the task list. And the task list is just it's a one-dimensional data set with one row for each chunk in the data set we're going to write to. And as the worker pods are working, they grab a row from this task list that identifies which chunk they should update. They update it, and then they mark that row as complete, right? So the flow for a worker pod is get a row from the task list that hasn't been written yet, write to the chunk in our target data set, and mark the task list as that chunk has been updated. Okay, once there are no more empty rows in the task list, the job is done, and the worker node exits, basically. And we can see how this works in the code, if I can find it here. So we come through, we open the domain, we get this task list, and there's a magic function, get next chunk table index. And so let's look at that. So okay, so this I have this code work either with HSDS or HDF5. In the HSDS case, we say, I'm looking for a row where the status is 0, meaning that that row hasn't been touched. And I'm going to update it with start times now, status is -1, and the pod is our pod name. And then call this table update where. So now you're saying, hey, what's going on here? You would think you would just find this row, modify it, and write it back to the data set using your normal H5 commands. But the problem with that is we have multiple workers, and there'd be a high chance to have a race condition, right? That 2 workers would see that same row with status equals 0, and both try to modify it at the same time, right? So this update where is a special HSDS kind of function that works like a database semantics, right? It says, atomically, I want to identify this row where the start is 0 and modify it exclusively of any other client that's trying to do the same thing. Okay. Anyway, so then we go back here And the actual working is just pretty simple. I'm just going to write a random array for that chunk. And then we set this table to be done. And we go on and we keep on doing while true. Right. So when this thing is, actually, I don't remember how this worked. Yeah, I think when there's no more chunks, this will just we'll block here at the get next chunk table. So let's try this out. So I have more magic functions here. So recall we had 16 HSDS pods. So let's create 16 worker pods. And if we look at scale job, if we look at start job. Here, let me run this one first, just for educational. This code here creates the task table. And if we look at this, so I gave it a parameter of 50,000 by 50,000. So it's going to create a 50K by 50K data set. Oops. Didn't mean that. So we have a data set that's 50,000 by 50,000. And this task list table that's 5,000. It's 5,000 because it works out that there are 5,000 chunks in this data set, in this dset data set. So we have 5,000 tasks for our workers to work on. And if I look at this here, we do kubectl apply this job YAML. That'll start our worker. Actually, by default, you'll create one pod, one job pod. And then we do kubectl patch. And we're going to change the parallelism to whatever the argument is. Okay, so if I do start job 16, that goes off. And now if I do kubectl get pods, we have our 16 HSDS pods and our 16 HS perf pods. And presumably they're all doing good stuff. There's another script here called get status that basically looks at the task list and gives you an update on how much work has been done at any given time. So what's going on here? So this is our file. We have 16 pods. These are our worker pods. And each pod has done some number of tasks, right? So this pod has done 325. This has done 337. It's a little bit random, right? Because some pods start a little bit later than others. Some may have finished, a little bit earlier than others. But overall, they've all done around 300 of these chunk writes. We have 0 pending things to do, 0 in progress, and it took 29 seconds to run. Okay, so what does that mean? I've been trying to tabulate some results here. So these are all different scenarios. This was like on my laptop. This was on Azure with that 1 core node and 4 nodes. This was on Azure with this more beefy node called the D32. So we are basically here, right? We had 16 worker pods, 16 HSDS pods. We actually had 4 nodes, and 50,000 by 50,000, meaning 18 gigabytes of data to write. And it took, what was our time? 29 seconds, right? So with one node, it took 36 seconds. Adding 4 nodes made it a little faster, right? Because presumably with 4 nodes, I don't think the increase in CPU really matters, but you have an increase in overall network bandwidth, right? So each node in this cluster is getting work from Kubernetes. It's writing to HSDS, which is on another pod, possibly in another machine. That pod is writing to the Azure blob storage. So a lot of network traffic going along. Overall, we're getting, in this case, around 500 megabytes per second, or about 4 gigabits per second. And it seems like there's a kind of a cap here. Like when I was doing this run on the smaller nodes, if I went from 4 worker pods and 4 HSDS pods, it took like 130 seconds. Going to 8 was just moderately faster. And going to 16 was even slower, right? So I don't truthfully know exactly what's going on, but my suspicion is that you're hitting a cap in terms of network bandwidth that's limiting the performance. When we went to the larger node, so each machine type in Azure has a certain preset in terms of not just its memory and CPU, but also in this network bandwidth. And these bigger machines have a much higher network bandwidth. So when I run the same thing here, like 16 by 16, we went from 117 seconds to 38 seconds, right? And going from 4 pods to 8 pods to 16 pods, we saw our performance go from 75 to 54 to 38. But again, I think going from 32 to 64, you're pretty much capped on your performance. So again, I think here we're hitting the limit in terms of our network bandwidth, and adding more pods isn't really helping, even though our cluster has the capacity to run all these pods.
Mm-hmm. In your timing, I'm sure you've tried to factor out that artificial contention when you create that task list. And
yeah, I only thought that in this just like an hour ago when I was looking at this again, because I noticed when I'm creating, so we do this get pods, we got all these pods. So these worker pods now are in this completed state. If I do like start job 64, or let's go crazy, let's do 128. When I do get pods, you'll see that there's this startup time, right? So a good part of this 30 seconds, when you're creating a large number of pods, is you're waiting on Kubernetes to schedule all these workers, right? So that's not really fair in terms of gauging the HSDS performance. Right. So I was thinking it'd be better if I arrange it so I can create the worker pods that can get into a ready state, but not start work until the starting gun goes off, whatever that means. And then we would see, basically how fast the inherent HSDS bandwidth was in that case. But I guess, Gerd, you're talking about something else. You're talking about contention for getting this task from the worker before it even gets to writing the chunk itself.
Right, because and the contention will just be increasing the more parts you have contending for that table to get entries assigned or chunks assigned. And I mean, it's both. There's what you are describing here, spinning up that pod and that worker pod, and but then also initially assigning work.
Right. So this is kind of gets to the architecture for HSDS, right? So again, if I look at these pods, imagine we're doing this this table selection to get the task for a worker pod to work. The chunk for that table is owned by exactly one of these pods, right? So however many workers you have, it has to go to that pod to do the update for that task. Now, I suspect that that's not really going to be problematic for any reasonable number of workers, but I should actually time that and see how much time we spend and what the limits are for n number of workers doing this this query update, right? Because theoretically, right, if you have gazillions of workers, but only one pod can handle that particular request, that's going to be a limiting factor.
Right. And if you want to throw in another task management framework, I mean, you could use something like Spark to create these tasks rather than Kubernetes. I don't know what the performance difference is, but yeah, PySpark. I mean, you could do the same thing with PySpark.
Right. Yeah. I think though it's interesting in a way to use HSDS for everything. I guess in a way we're doing things like a ZeroMQ would do, right? And HSDS has this functionality, and there's some convenience of only needing to configure this one thing, right? HSDS, rather than HSDS plus Spark or HSDS plus ZeroMQ, and so on. The other nice thing is like this get status function I had before is you can write this just with HDF, right? You don't need to use, so I could have this task list done in a MySQL table, right? And do SQL code to do the same kind of functionality. But then to view that table, I would need to use SQL, right? Here, this convenience is you just stay within the kind of HDF frame of mind for all these things. I'm not saying it's better. I'm just saying it's just one way to approach it. Alrighty. So I've been blabbing. Any questions on this, or any questions in general? So I think this is it's an area that I find interesting because it kind of highlights some functionality that is harder to do, or at least hard to do in exactly the same way with the regular HDF5 library, right? So here we have multi-writer, multi-reader, and these various workers are coordinating without any special extra functionality, right? There's no kind of super global coordination function, right? They're all those kind of workers doing their stuff. You can bring on more workers anytime. You can scale up or scale down the number of nodes in your cluster. And it all works in this very cloudy, kind of decentralized manner, right? Which is, my limited experience, it seems a little different than how MPI jobs work, which are usually in a more coordinated fashion. So I think in the future, I will, I want to do this thing where we start all the workers at the same time, and then also looking at measuring how much time we're spending in this table selection versus the actual writing, and what the limit of that is. All right, so I hope that was mildly interesting for everyone. Let me know if you have any other questions. Feel free to send a question to the HDF Forum. And I guess that's all we have. Anything else, Lori?
Nope, that's it. We'll have Alexander this time next week.
All right, awesome.
Thanks,
Thank
John.
you, everyone.
Okay,
Good
there you
night.
guys.